Excellent. So welcome all. This is meant to be a discussion session. So our aim is to say just enough to get people talking and no more than that. The topic for this one is understanding the origins of FRBs. So we've got Shivani, Jason, myself, and Amanda here with the ultimate, we're the ones with the conch horn at the moment. We're allowed to speak. So let's get into if I can move along here. So essentially, if you want to speak, raise your hand. We can unmute you if we like you enough, and that'll give you the power to speak. And if you say not very nice things, we'll ungive the power to speak. And then let us know if you want to, share a plot, right? If you've got some interesting plot that's relevant to the discussion, let us know and we can promote you to screen sharing ability. Post in the chat for small side conversations. There's Q&A on Slack. Please keep the conversation going. Have side parallel discussions. That's all good. And if something particularly interesting is said or posted by somebody else somewhere, bring it to our attention. All right. So this is meant to be asking about the origin of FRBs, right? But what do we mean by origin? So there might be very broad classes of models, such as from neutron stars or accreting black holes or cataclysmic merger events, which are fundamentally different. But even if we said they're neutron stars, well, are they like magnetars or normal pulsars or millisecond pulsars or accreting objects, right? And of course, multiple models can make the same progenitor, right? You could have mergers, like it's still plausible that two low mass neutron stars could merge into a stable neutron star, right? Or a supernova can make a young magnetar, right? And then of course, at the finest level, there's the specific emission mechanisms, Crab giant pulsars, normal pulsars. So when we're talking about what are their origins, are there multiple origins, it's a little bit difficult where we draw the line. So we're going to try to discuss all of these things. So broadly, we're dividing this discussion into the high level, the source models and the population studies. So this would be, do they seem to be like they're a neutron star population or something like that? Then the microphysics and the details of emission mechanisms. We'll conclude with multi-messenger observation. So this was, I think, session 6, which I haven't had a chance to watch yet, but hopefully many of you have. And then the final question is, well, this is intrinsically interesting, but what do we actually need to know about the origins of FRBs to be able to use them for cosmology? So I'll just introduce the first topic. Then Shivani is going to show a bunch of interesting plots, and then we can let ourselves wander off there. And we'll probably allocate about 40 or so minutes for this broad topic. So when we're sort of broadly talking about statistical population properties, right? You might imagine looking at host galaxy properties, right? Their star formation rate, what kind of galaxies they're in, and where in the galaxies they are, right? The offset distributions. You can look at the cosmological evolution of the sources, right? Do they evolve with the star formation rate or star formation rate plus a time delay? You can look at the properties of the repeaters, right? If repeaters are expected to age somehow, or maybe they spin up, right? If it's a merging binary, right? Maybe they're not aging, maybe they're spinning up. And my point here, of course, is that it's important when we want to do this is to monitor the boring sources too, right? So if we only monitor the bright, rapidly repeating objects, we won't be able to probe something that might be in a dying off region. And of course, there's a bunch of observation bias issues to discuss here, right? I just put in a couple of examples of observation bias. It's easier to associate a low offset event with a host galaxy than a high offset event. And, high DMFRBs from the inner regions of a galaxy or the distant universe are tough to detect. So with that broad thing, I'm going to hand this over to Shivani, who can kick off with this slide. And then Shivani, when you think it's time to hand it over to everybody to start discussing thoughts and opinions, please go ahead.
Yeah, thanks, Clancy. Yeah, so I want to discuss about the host galaxies of FRBs that we have been detecting. So the plots here only include the FRBs for which the association is pretty secure. So I'm talking about path probability of greater than 90%. So that kind of includes 16 hosts, of which 6 are repeating and 10 are non-repeating. So if you look at this plot, which is very famously called the color magnitude plot, it kind of tells you about the overall stellar populations of the field galaxies and then compare them with the FRB host galaxies. So this cloud here is the blue cloud, where most late type galaxies and star forming galaxies and young stellar population lives.
Shivani, I just realized that because I'm sharing the screen and you want to be able to use your pointer, I'll unshare, you do the sharing for this so people can see your cursor when you're pointing.
Right, okay.
I think it's going to be better that way. We're initially planning on having me being the one to screen share so we don't have to cut in and out, but I honestly think it's better if you can then point at things. And then it helps me to be able to monitor chat and Q&A.
Oh, that's the wrong one. Wait, stop. There are too many pictures on my screen. Okay, so can you see the screen now? Can you see the screen?
Yep.
Okay. Oh, I'll go to the present mode again. Yeah, so as I was talking about this color magnitude plot, so we are seeing that FRBs are not living in the red cloud. So most of the galaxies are like in this plot are blue, and then there's kind of a transitioning region where the galaxies transition from being star forming to red and dead. So basically quiescent galaxies. So over here, the galaxies which live here have old stellar populations and they are red in color. So if we assume a mass to light ratio of 1, then this axis here can be is similar to what you call the stellar mass of the galaxy. So this is how luminous and how massive the galaxy is, and this is UV light. So okay, so this is one picture, and you can see where all FRB lies. But when you take when you weight these galaxies by their stellar masses themselves, then this picture kind of shows you where most of the stars are living in the near redshift universe. So I should mention that these background galaxies are in the redshift range of 0 to 0.5, and the FRBs are in that range. So it's okay to compare them with each other. Yeah, so if we come back to this plot, now here you can see where most stars are in our near redshift universe, and you can clearly see that there are not many FRBs in this red and dead zone where most of the stars live. So does it mean that we are seeing an apparent dearth of FRBs in these red massive galaxies? And so first thing that we can discuss about this are there any observational biases at play that we haven't encountered or we are unaware of that could lead to this kind of results? And if FRBs are not really living in the older population dominated red and dead galaxies, does it mean that FRBs are not solely dominated by these delayed channels? So by delayed channels, I mean the kind of channels where there is a long delay up to like a giga-year or more than that between the actual star formation happening and the FRB progenitor being born. So those channels include such as magnetars formed by accretion-induced collapse of a white dwarf or neutron star mergers. But if we look at that and then we compare the results of this R47 or this galaxy M81, which was localized in M81, and it's coming from a globular cluster. So that kind of challenges this interpretation, because then if it's coming from a global cluster, it has to be an older stellar population. So it's kind of interesting, and it will be good to discuss about this thing. So the next thing we notice is that FRB hosts are similar
Manny,
to
there's
our
a couple of questions that came in, maybe related to what you're saying. So
okay, because I had the shared screen.
Yeah, I can read them out to you.
Okay.
Moet already has raised the question, what do you mean by nearby universe? So again, we're already starting to get into the definition issue.
Yeah. So by nearby universe, I'm only selecting the galaxies up to a redshift of 0.5. So all these background sources that you see, these background galaxies are Primus sample of galaxies which are in the redshift range of 0 to 0.5. So that's what I meant by local universe.
Yeah,
like
not extreme local universe like what Moet is looking at right now.
Yeah, we have there are different definitions of what you mean by local depending upon what you do, I guess.
Yeah, but here out to 0.5, which for a cosmologist would be nearby universe. Yeah. And then Sergey is asking, can we exclude that FRBs in the red zone are not in globular clusters or similar dense stellar structures?
Yeah, so
yeah, sorry, go ahead.
okay, yeah, so that is something we can discuss in the coming slides, because I have looked at some of the massive elliptical galaxies, early type elliptical galaxies, and I've looked at the distribution of globular clusters, where these globular clusters lie in those massive elliptical galaxies, and then compare them with the distributions of offsets what we see for FRBs, and they're not at least statistically consistent with that. So, and also the globular clusters, the thing is that, so there are two populations, whether it's a disk population or is a halo population. So the other thing that we need to investigate is the way that we associate, we find a probability of association for an FRB using path. So such method, do we really say that an FRB is associated with a galaxy if the offset is about 100 kiloparsec away from the center of the galaxy? That's where most of the halo population of globular clusters are and older stars. So yeah, this is something that we still need to investigate. But with the current sample, I don't know about globular clusters, but we are not finding FRB hosts which are red-ended galaxies. So yeah, hence the conclusion that they might not be dominated by these delayed channels.
Sergey, did that appropriately answer the question, or would you like to make a more extended point? Because we do have the power to let you ask that.
Yeah,
yeah.
We can discuss.
Sergey, if you want to say something more. Right, okay, I think that must have answered Sergey's question then.
Okay.
Using you, right. Sergey.
Yeah, so that was that discussion about finding a dearth of FRBs in massive red galaxies. But then on the other hand, we see that most of the FRBs are lying in the Green Valley region and star forming region, and their mass is similar to what we see for Milky Way. So, and then again, that raises a question whether the Magnetars or FRB progenitors, they are formed by fossil channels such as core collapse supernovae. Are they the dominant progenitors? For example, the detection of this FRB-like burst from the SGR supports that claim. So are we seeing a mix of delayed and prompt channels in the way that you can create an FRB progenitor, or it's solely dominated by one and non-dominant and completely ruled out the other? So, see some questions? No. Okay. So I'll move on. So this was just comparing the FRB host galaxies with the underlying population of field galaxies. But now, again, we can compare them with transients as well. Yeah, so here, what we are doing, we can compare FRB host galaxies with other transients, and that's what have been done in these two papers by Mannings and Hines. So when they looked at the host offset distributions of FRBs so here projected offset means the physical offset between the center of the galaxy and where the FRB is. And yeah, so when you compare that with that of other host galaxies of other transients, you start to see that LGRVs and superluminous supernovae are not statistically consistent with FRB host galaxies, and the properties of core collapse supernovae and SGRB host are kind of consistent with what we can see with the current data. So yeah, so then that brings us to the question of our ultra prompt channels for producing young magnetars are completely ruled out, and FRB2021 is an outlier in the population. But then when we think about that, and then we learned in the conference that there is a twin to the repeating FRB-R1. So that's interesting. So that's basically telling us that there are multiple ways in which you can create an FRB progenitor. Yeah, so I'm happy to discuss more about this if there are questions and
Can I make a comment about that point, Shivani?
Yeah.
And this is kind of related to what Clancy was leading off with a bit as well. I think I think there's the possibility that we've really, despite the fact we've been observing them for over 50 years, really been underestimating what neutron stars can do. And all the pulsar people on the call, of course, will say, you know, we see various types of radio pulses from pulsars. We talked about this last year a little bit as well. And I think we've been biased as a community a little bit to think that FRBs are these exceptionally bright things that must come from exceptional events, and that, you know, it must be very special types of neutron stars and whatnot. But I'd like to hear, especially from the theorists, maybe we've just been really underestimating neutron stars. Now we're just realizing that neutron stars can do all kinds of things and all kinds of timescales and luminosities. And then this makes that whole discussion that we're having right now very, very difficult to solve, because it could be that that we're easily seeing like half a dozen different types of emission mechanisms from neutron stars, right?
Yeah, exactly. Yeah. So,
Jason, I just want to expand on that point. That, to my mind, such population studies, like if we had a very good population distribution of neutron stars in other galaxies, we could repeat this. But of course, we know a whole bunch of neutron stars in our galaxy, but it's very biased towards our local part of the galaxy. And of course, people search in different regions, right? It's not complete. People know there's more in the galactic plane, so they search more in the galactic plane.
Yeah, that's right. And for a long time, people were looking, for instance, like nearby galaxies like Andromeda, try and find a super crab there. It was really biased towards what we knew about in our own galaxy. But maybe, like I said, we've really been underestimating what neutron stars can do in general.
Yeah, so I just see there's a comment or question by Sriharsh, who says that the offset distribution result has a caveat that it assumes a dominant channel, right? Which is a good point too, right? That may not be true if FRBs come a large variety of different channels. So I guess, Sriharsh, your general question would about how any ideas on how you can do that. Well, would it be correct that if it's, let's imagine that 10% of the FRBs come from short gamma ray bursts and 50% from calcium-rich transients and 30% from type 1a supernova, you would still be able to combine your curves there, right, Shivani, to try to work out what combination of those curves would fit the FRB cumulative distribution best. That would be something that wouldn't be terribly difficult to do. I mean, it'd be a little bit annoying. But yeah, I imagine, it would be simply a case of, I guess, fitting the observed cumulative distribution as, A times short gamma ray burst plus B times long duration GRBs, etc. But of course, do we have any prospects, and maybe I can ask this to everyone, that, well, no, they're not, but they don't need to be orthogonal, Sriharsh, they just need to be different. They need to be non-degenerate.
I would read out what Sriharsh is posting in the Q&A, because I think only the panelists can see that. It might be better, actually, if we just encourage people in general to put comments in the chat for panelists and attendees, then everyone can see the comments. Oh,
that's a good point. Yes, apologies. So Sriharsh's comment was that they are not orthogonal basis vectors, which is quite true. But as long as you can't describe one of the models completely by a linear combination of the others, you can still have some resolving power. But Sriharsh was quite right. We probably need an extremely large number of FRBs here to be able to really start doing that kind of analysis. Yeah, so what I was going to ask is, does anyone know how we can construct one of these predicted curves for neutron stars?
Yeah, I think that's what Chimes et al. Has done, at least with the offset distribution of where neutron stars are in the galaxy when they compare it with the offset distributions of FRBs. And I think he's also on call, so maybe if they want to speak more about that.
I'll give people time to post requests. Oh, by the way, if someone puts a hand up, how do we see it?
In the participants window. I'll keep an eye on it as well. Ashley, if you want to respond to Shivani, you're permitted to talk if you want to, but you don't have to.
So since I'm sharing my screen, I can't really see the names of the participants and allow them to talk.
Yeah, I've allowed Ashley to talk.
Hi. Sorry, I missed that. Did I request to be able to talk? Or?
It was forced upon you, Ashley.
Okay, right, fine.
Sorry about that.
Was this about our paper recently that we?
Yeah. So
yeah. Okay. Yeah. So we did look at this distributions of pulsars, Xray binaries, magnetars in the Milky Way, in terms of their offsets on the galaxy and that kind of thing. So yeah, I'll suggest checking that out, that paper. But yeah, if we looked at this, and basically we find that FRBs kind of best match the magnetar distribution. The caveat is that there's large uncertainties on their distances, and there's questions about how complete the sample is. But overall, yeah, it looks as though that the FRBs on their hosts, in terms of offsets in close fluxes, fraction of light as well, we did. They do match galactic neutron star populations. Within the uncertainties.
So maybe it's worth reading out. Sorry. Maybe it's worth reading out the discussion that Barak Zakai is having in the comments, especially as it connects to what Jason was saying earlier on. Sorry, I have my video off because my internet seems very unstable the second I switch it on. So I'll just apologize for that. But to Jason's original point about neutron stars possibly showing us more physics than we had originally thought, I think that's one of the insights we're getting from gravitational wave data, which is that there's just more that can be seen than we had expected. And Barak has asked that if FRBs are just a manifestation of regular neutron stars, where are the galactic ones? Why aren't we seeing FRBs, very, very often from within the galaxy if they're just from neutron stars? And if they're not from regular neutron stars, then what is the irregularity that they derive from? Does it require a special age, some special condition of formation, some weird binary? And I think it's a very good question that's maybe worth tackling in this setting, especially as there was such excitement to see a FRB from a galactic magnetar or neutron star recently. And so there was great joy to know that it could be done, but why does it then not happen all the time? If something is possible, why isn't it common? So I don't have a good answer for that, especially because they are then at exceptionally low redshifts. We should be able to see them all the time.
Well, can I make a quick point on that? I mean, the galactic magnetar also made a bunch of kind of intermediate bright bursts that for galactic neutron stars would be, exceptionally bright, but would never be seen from extragalactic distances. So I think we also have an issue in terms of, when is a radio burst not bright enough to be an FRB anymore? And that source really fills in the parameter space.
But in some sense, that's a selection bias because it's bright enough if you're close enough, no? So we're close enough to this one that it was bright enough.
Yeah, well, related to what Clancy answered, I mean, from extragalactic space, it's potentially we're just seeing the more rare events from these sources.
Yeah, so there was that talk. Sorry, I'm terrible with names and I forget which session, but looking at this giant pulsars from this, and I think this is the one you mentioned, Shivani, right? Was it 1905-20, looking at an analog with giant pulsars from outside the galaxy, it's observations from Meerkat. And there, there was no downturn in the giant pulse luminosity distribution, right? It was just a power law that kept going until people ran out of statistics. And as far as I'm aware, that's similar for the Crab as well. So if you just take neutron stars that produce giant pulsars and keep on extrapolating that power law, where do you actually get to? I mean, I know it sounds dumb, but it's simply a case of, and I remember when the galactic event was, the soft gamma repeater was plotted, the rate of a burst like that was shown there. All right, I think Sergey's asking to show a plot, so let's see if I can.
Yeah, and Ben Stumper's had his hand up, so I permitted him to speak.
Okay, and then I'll...
And then maybe let Sergey show a plot after that, yeah.
Yeah, so just a quick comment on that for the Crab, at least. We've had been monitoring the Crab for a long time, and we have of the order of 1 million giant pulsars now in our data set, which I think, you know, even there at the highest, at the brightest end of the distribution, the statistics are still very poor in being able to fit the power law all the way out to the highest energy. So extrapolating from there is always a bit of an issue, even with 1 million. So I think, you know, I think you've got to be careful about extrapolating those power laws all the way.
Well, we've got to be careful about extrapolating. We can stop there.
Well, yes. In this case, we're discussing crab power laws. So
yeah, but Ben,
yeah.
Ben, I mean, another issue though is like, you know, we have one crab and we live on a particular planet. I do wonder at what level beaming is important. If we lived on a different planet, that the crab would either be, you know, pretty garden variety or not even visible to us, besides the nebula, or if we lived on a different planet, that we'd see even brighter giant pulses from it, right? So.
Oh yeah, sorry, I'm not arguing that it can't be giant pulses. I'm definitely not arguing that. I suggest I might write a paper that says it might be, but what I'm just saying is that you just need to be careful about taking these power laws and just extrapolating them and saying, oh, that means you can get a pulse this bright. And you know, I'm sure the theorists are shouting at us right now that there's only so much energy you can extract from the spin down of the pulsars to power these things. So that's the other thing you need to take into account.
That's true, but for maybe some of MOET sources at tens of megaparsecs, it still works.
Maybe it's true.
Sorry,
yes.
just quickly, Sergey, is this you showing this plot at the moment?
Yes.
I can guess what it is, but I'll let you describe it.
So I think that this plot can be an answer to the question about galactic FRBs. And why don't we see something like this from galactic neutron stars if they all produce it? Well, now we just know that not all of them produce it. And this plot is very optimistic, I would say, to those who believe that Magnetaries are responsible for the majority of FRBs. And it's nice that you can put in the same plot FRB statistics and the only up to now point related to the galactic flare, and it fits. So the first flare we see is not an outlier. Maybe, of course, it's just a game of statistics, and when we collect more, some problems can appear. But still, it looks like everything fits inside the error bars. And looking at such plot, I don't think that we, at the moment, that we face a problem that population of Magnetaries cannot explain the majority of FRBs, the general statistics of these sources.
So again, just to pick up, as some people are, when they're sending messages, it only goes to the panelists. So Barak, your response we could only see, which is that if you have STARE or other all-sky surveys, why don't we see the 1 per year crab pulses? Do we really not have an end to the power law? So just that's the question that if any of the STARE people or all-sky survey people are here can maybe answer. But just in general, if people can try to remember to send when they're commenting in the chat to try address panelists and attendees so everyone can see the discussions. I will keep an eye on the chat though and try bring the discussions into the general chat. But is there anyone who wants to comment on that? On STARE, obviously, not on chat etiquette.
I mean, one maybe it's a bit of a cop-out, but one of the issues is STARE does not have amazing time resolution. So I think, well, this will come up in the next discussion session, that there's probably a whole population of much shorter duration radio flashes that we're completely missing right now. But I would also say that, you know, we only have one crab, right? So we're not necessarily on the optimal planet for observing the crab.
I don't know if occasionally Maxim Lutikov is around. I can't see the list of participants. People like him might comment, because it seems that to produce a mega Jansky flare for crab, it's necessary to have some extraordinary parameters of this bunch of emitting particles. And probably just with parameters of the crop, this neutron star cannot support such bunches. So I agree that maybe this power law can, exactly for the crop, cannot continuously go to very intense flares. But of course, it's better to ask people working on neutron star magnetospheres. And at the conference, there were several theorists working on the subject.
I see a message from Ben saying that CHIME has shown in the past that they have sensitivity to the crab when it is above the horizon for the brightest bursts.
And similarly, I believe, was it Utmost that saw a crab burst in some ridiculously far out beam?
Yes,
I actually don't know if that's been published, but so in theory, there are instruments that are, have a much wider sensitivity than their nominal sensitivity to very bright galactic bursts, because you might be able to see something extremely bright in your, as we saw from the CHIME observation of that. Yeah, Vivek, are you online at the moment? Want to say just something about this very bright crab burst that Utmost saw? I would like to make a broader comment though while we're seeing it. Oh yeah, there's one hand up. Broader comment, which is simply that, I'm very much an experimentalist here. And until I see an observed statistical downturn in the power law from the crab, I'm going to say that it's plausible that it goes right up to FRBs, right? It's just that it's once per 100 million years, right? Per crab-like object.
Yeah, so I can comment a bit on this Utmost pulse. So it was kind of a couple of years ago, 2019 February. We were pointing 72 degrees away from crab with Utmost, and we saw a giant pulse, which we didn't expect to see from crab. We thought it was an FRB with a very low DM, but it actually turned out to be localization up matched up to the crab's location, and the DM was exactly crab's. Now we didn't imagine at any point in time that we would need to model our beam shape 72 degrees away from our beam center. So we didn't have a good handle on how bright it was. We tried some test observations, and very early estimates were suggesting that this burst had a fluence in megajansky, upwards of 1 megajansky. However, we had to repeat measurements to ascertain that this was the case. The error bars were currently of the order of magnitude, so we couldn't claim it was a megajansky or 100 kilojansky. So we tried repeating observations, and they were always limited by RFI. So we kind of gave up on it at the point that we were not able to ascertain the flux density or the sensitivity of Utmost 72 degrees from both sides. But if some other telescopes, I know I did get in touch with Ziki, I think a couple of years ago, and they mentioned that CHIME had seen the same burst, but it was early days for CHIME as well, and they also had not calibrated their sensitivity in that side over the time. So there could be such 1 in a million events that might come through now that we have active wide field surveys going on. We should keep our eyes open for these.
So speaking of wide field surveys, I've got a very experimentally motivated question. So let's imagine that instead of a megajansky burst, which is incredibly bright, but it's nowhere near as bright if it's a galactic megajansky burst as an FRB, which if you move it to the galaxy would be, some of them would be terajanskys or more, right? Probably even more. If you have an instrument, right, that's looking for dispersed pulsars, and it gets some incredibly bright event coming in, if that saturates the receiver at the analog level, then you're not going to be able to measure the correct frequency information, right? It'll be completely smeared out. And if you don't measure the correct frequency information, you can't find a dispersed sweep because it'll just make everything go crazy for some period of time. So could it be possible that we have had telescopes that detect incredibly bright bursts at some massive level that have saturated the instrument and therefore don't look like a dispersed sweep? Is that a possibility? I don't understand the instruments quite the level of detail to know when this effect would kick in. I
think that I see Ben and it seems like also Ron have perked up about this. Let me just mention briefly, like we've been doing this recently, actually a master's student in Chalmers University in Sweden, Olaf Forsen, has been working with Frans Kirsten with a signal generator to basically map out at what point we would be missing bursts. And it could be because of the the signal chain at the telescope could even be because of digitization that you do in the search processing. If you downsample to a smaller number of bits before you actually search the data. And I think we're pretty confident that we can get up to mega Janskys without too much hassle. But terajanskys or above terajansky, then I think it starts to get really hairy. Maybe Ben has done something similar.
I'll let Ron speak first. He's probably got much more sensible things to say about the radio astronomy side of things than I do.
Have we promoted Ron to speaking ability yet?
I just gave him the power.
Oh no, what have you done?
I can also take it away, Ron. Oh. Didn't seem... Do you have any experience with this, Ron? Saturation from very bright events.
Well, it looks like Ron's made a comment just to us in the panelists, pointing out that he was going to comment that the Lorimer burst was initially excluded because it was too bright. Although in that case, that was excluded from a human perspective, right? Well, it was both the human perspective and the search was only looking in a certain range of brightnesses. Is that correct?
Sorry, guys. I was busy making my dinner and I didn't have a microphone connected. So I missed a little bit then, but all I was going to say is that pretty interesting that the central beam for the Lorimer burst was rejected because it was so bright it had to be RFI. And if it hadn't been detected through a side lobe, we would never have known about Lorimer. So this bias is absolutely present, no question.
Okay, interesting.
Sorry, Clancy, I just wanted to check the point you were making about the frequency side of set. I don't think the saturation will affect the frequency response. It doesn't. So I don't think it will prevent you from detecting a dispersed burst. It might mean it gets rejected as RFI, as Ron was just suggesting, or it might mean that, as Jason was suggesting, it hits the limits of your digitizer. But if that's the case, if it hits the limits of your digitizer, you'll still detect it. You just won't know how bright it was intrinsically.
Yeah, if you're doing machine learning classification of events, though, these saturated things look like junk, so it could get thrown away. It kind of takes, at a certain point, you could imagine that it kind of takes like a Jocelyn Bell to look at the data and say like, this isn't the normal thing. This is something special.
And then if we're looking for intrinsically rare things, then it's unlikely we've actually got the human time to eyeball everything, right? And so we probably are using, lots of automation in terms of, either it's machine learning or cuts on the parameter space. So maybe it will be very difficult to search for such things.
I see a comment from Bart as well. So maybe if we can give him the talking privilege, they can talk about that.
Hello. So I was thinking about so can you hear me?
Yes.
So I was thinking, so if you extrapolate the rate of the crab pulsar, what is the expected rate of FRBs? Like how long should you wait on the crab in order to see like these run-of-the-mill FRBs? Is it 100 years? Is it 10 years? Is it 1 billion years?
So Ben, you mentioned that you had lots of statistics on the crab. All right. Whoever's sharing this, please describe.
Yeah, sorry, it's me. I think that you just continue this plot till you reach whatever fluence you like. So numbers are here and the rate is per hour per decade, per dex. So you can continue and maybe count faster than I do.
And that power law is a differential power law, right? So it's dn on df, or dr on df is our, or is it rate above a certain? amount. I should be able to.
Might be dn, yeah.
So how many orders of magnitude we need in the horizontal axis in order to get to FRBs? 3? Something like this?
think
Well,
of a
for
lot
luminosity,
more than
you
3
need, well, orders of magnitude. And so you might wait for quite a long time. So the idea is that crop itself might not be, well, if we just have all neutron stars similar to crop, we cannot explain FRBs. We need neutron stars with a larger field and shorter periods. We can calculate their fraction under some standard assumptions, and then you can obtain interesting numbers. But what you probably cannot do, you cannot explain very large luminosities in principle. So if you have FRBs beyond several hundred megaparsecs, then I think it's extremely difficult to explain them by giant pulses. The whole idea is starting from that nice paper by Cordes Wasserman, which was really a detailed study. They spoke about distances up to 100 megaparsec, if I'm not mistaken, something like this. At that moment, it was not clear that FRBs are much further than the distance.
So basically, you're saying that we need something rarer than the crab.
Yeah, we need more
Rarer
active
in what
neutron
way?
stars.
But as Jason said earlier, we don't know whether we've got an optimum angle to the crab if it's beamed. So I would think, since we don't have any idea about the beaming angles, we can almost pick whatever brightness we want. We just assume smaller and smaller beaming angles and they get rarer and rarer, but there's no energy problem.
In principle, yes, you are right, but it's a little bit ad hoc hypothesis, isn't it? We use some hidden parameters, and of course, with 1-2 hidden parameters, we can fit everything.
But then why Sergey, are magnetars more natural in your mind?
Well, in the first place, because now we saw one flaring. Before, of course, it was also just one of hypotheses. But as for magnetars, I think that, well, we don't understand completely the mechanism of giant pulses. But at some moment, it became more natural to think that FRBs are related to the release of magnetic energy, and you need lots of this energy. So magnetars are better sources from this point of view. We know that they can do it. We know that they make flares at high energy, but with luminosity 10 to 47 ergs per second, with a characteristic duration of tens of milliseconds, and with very small scale periodicity. As far as I understand, they cannot measure nanoscale periodicity in gamma rays or in hard X-rays, but it looked like they are a good tool to produce something similar, and we needed just a tiny fraction of their total energy release to explain this radio emission. But I totally agree that before April 2020, it was magnetars were just one of hypotheses. But can I make a very short comment on magnetars? We started with discussing origins, and I want to underline that we don't understand origin of normal magnetars. So it's not for granted that just in 10% of core collapse supernova, we obtain a magnetar. It's absolutely not clear. Maybe there is something special even about normal magnetars. We don't know how their fields are enhanced. And note a funny feature. We know about 30 magnetars, and none of them are members of binary systems. For neutron stars, it's not normal. 30 is a big number. And to have 30 isolated sources, activity of which could be easily detected in a binary, because nothing prevents to see a soft gamma repeater flare in a binary. You have to start to think that there is still something special about magnetars, and maybe even for magnetars we need something else. Maybe they are born from stars which experience coalescence of normal stars and binaries. So there are different ideas about this. And if this is the case, then it slightly shifts magnetars from normal relation of core collapse rate. So I would not be surprised if magnetars do not follow exactly all correlations typical for average core collapse supernova.
Sergey, a question about the idea of magnetars arising from merged stars. Do we see, would that imply that we might see magnetars inside globular clusters where there's a higher interaction rate? Or would the stars that are still alive inside a globular cluster be sufficiently small and old?
Well, stars might be massive. In globular cluster, if you merge two stars with solar masses, you don't obtain a neutron star at the end. So you need to merge stars with at least starting with 5, 6 solar masses, and then you can get a neutron star at the end. So yeah, globular clusters do not work in this sense.
And do they work in the sense when there is R accretion happening to the white dwarfs?
It might, yeah, but the rate is too low. Because even the supernova 1A rate is 1 order of magnitude lower than the core collapse supernova rate. So the rate of 1A supernova is similar to magnetar birth rate. And accretion-induced collapse are much rarer events than supernova 1A.
Maybe it makes sense, Shivani, for you to move to some of the other slides that.
Yeah, I think we have basically discussed what I was suggesting in those other slides. But yeah, I can reshare my screen. Yeah, and so talking about magnetars, we talked about magnetars. What about high mass Xray binaries, which were suggested progenitors for that particular burst R3, which was localized to a spiral galaxy, and it's offset from the very star-forming region. So yeah, and then there are theories proposed for ULXS system, ultraluminous X-ray binaries. So that's something we can again discuss. So, and then I just had the same slide about the rates and few plots. So if not non-neutron stars, what other exotic cataclysmic models can still produce FRBs, and what of those models can be ruled out in terms of what we know for rates and energetics? And I think we have slightly touched upon this as well. Are there any more comments and discussion about that?
Well, Shivani, I was just going to ask you, I see there's still some comments going on in the chat about the previous discussion, and that's great. People should absolutely do that. Okay. But when you say rule out some cataclysmic models in terms of event rates, I mean, we already know that we can rule out these as explaining the majority of FRBs purely by the fact that there's lots of strong repeaters, right? And cataclysmic models tend to predict, even if there are multiple bursts near the point of merger, it's over a short period of time, presumably. But then in terms of, are there one or two populations? Well, why not a second population that explains 1% of the bursts, right? Or, 0.1%. I mean, we're already seeing that CHIME, has just got so many bursts. Now they're almost at the 0.01% level that they can probe extremely rare things. So I'll come back to this later, but, something that we do want to also ask ourselves is how much time do we spend chasing the weird, interesting things like one FRB out of several thousand that shows a sort of sub-second scale periodicity, and how long do we spend just looking at the bulk of the population, whatever, whatever an average FRB means.
Yeah, those are all valid points. So do you want to take over, Clancy, and talk about source evolution?
Yeah, I'll just speak to this slide. All I really wanted to point out here, of course, is that the other angle that we have for tackling models is to try to model how the FRB rate evolves with redshift, right? So if it's events that evolve very closely related to the star formation rate, like supernova, are fairly well correlated with it, versus, let's say, something with a large delayed merger, right? So I like to think I've made a good case that there is source evolution, but at the moment it's at a very coarse level, right? So you can't really distinguish between saying that scales with star formation rate and something that scales as 1 plus z to the 1 power, right? We're not probing any turnover in the distant universe. And also point out there's, this paper by Cow et al. 2018, and I think there's a more recent paper by somebody, looking at trying to limit the delay times, right? But I also suspect that with our current level of knowledge, we can only put a very coarse limit on FRBs coming from something that's, begins at some star formation rate, but has a very broad delay time distribution. So I do think this is a way of tackling it. I'm not sure how sensitive that's going to be in terms of differentiating between different models. So if anyone has any strong opinions on that, but that was all I wanted to bring up. So there's a conversation still going on between Barack and others and Ron. So Ron, first of all, you'll note, Ron, when you ask a question, it's got this little 2 button above there, and I think you've got it only to panelists. So, Barack is currently a panelist, but Ron has asked you the question of why. So
I did not see the comment of Ron. So
yeah,
I did not.
Yeah, fair enough. So do you want to answer Ron's comment or read out your initial comment on explaining it with observation geometry and then address Ron's question?
Yeah. I don't know what is Ron's question, but I can repeat my statement. So
please go
ahead. So suppose you want to explain FRBs by saying, okay, maybe it's a crab-like pulsar, but maybe we are not at a favorable observing angle to see such bright bursts, because maybe we are at the beam edge. So my statement is that if we see 10 millisecond FRBs, these cannot be a super small viewing angle if you explain the cutoff of the FRB by just rotating out of the field of view. Because then these 10 milliseconds have to be some big fraction of the rotation.
And my comment, and thank you, Clancy, for pointing out that I hadn't changed this damn thing to everybody. My comment was that it may not be rotation, Barack, so I don't know we can impose such a limit. In the case of the crab, yes, you're right, the rotation, but we're just talking about FRBs and beaming, then it may not be, it probably isn't a rotational effect, in my opinion.
So in regards to rotation, the position angle of the polarization is something that often gets brought up. Is this telling us something strong at the moment? I know that in general, like Ray Lau presented his result that there was this one repeating FRB seen by FAST where sometimes you would have a flat position angle across the burst and other times there'd be quite a slope. Actually, what I might do is I might introduce the next topic because this is leading on into the microphysics of the bursts. So my proposal to the other panelists is I introduce the microphysics aspect.
Yeah, so you can share the screen now, Clancy.
I'll do that. Okay.
So while Clancy's getting organized, this is anecdotal almost, but JP McCart was very enthusiastic about rotation models and was desperate to find position angle swings in the FRBs, and incredibly disappointed when, for the vast majority of cases, we don't see any swing. So it doesn't mean it isn't rotation, but it does mean there's no evidence for it.
What it really means is that if there's rotation, it must be very long compared to the duration of the burst. Is that correct? Ron, is that the right interpretation?
Oh, I was hoping one of the pulsar people might chime in because they're more used to this than I am.
I think Ben wants to comment on it.
Sorry, I guess I'm a pulsar person for this particular question.
It's not a pejorative term.
No, I'm used to it. No, that's not necessarily the case, right? It depends where you cross the beam of the radio emission, right? So you don't need to pass, you don't need to see the full swing, or the swing can be flat, and certainly in the case of magnetars, we know that the PAs can be very odd indeed. So I don't think it rules out rotation, and it doesn't necessarily mean that it has to be a long period thing. It doesn't mean it's not.
But can I underline that long periods exclude rotational energy losses as source of energy, definitely.
Yeah, that's a good point. And Ben, I wanted to make a comment about your beam crossing model. I could certainly believe that for any given, any given source, then we might be seeing it at a point in the beam where we don't see any PA swing. But if we were seeing no PA swing at all for 100 or so bursts, presumably that would be very unlikely.
Depends how wide their beams are.
Okay, I guess. There's a reason I'm not a pulsar person and you are, I think. Okay, let's, what I'm going to do is quickly introduce the microphysics aspect of this, which is just a continuation of the current discussion, really. So this was really brought about because I'm going to leave this quote here from Jason at the last FRB 2020. He said something like this, right? That neutron stars can do anything you want them to do. So if you point out all the weird things that FRBs do, there's a lot of them, right? So you can have FRBs with incredibly small observed bandwidths, right? And of course, there's a huge discussion with all of these about how much this is an intrinsic effect and how much it's due to something in the way, right? We've got beautiful sad trombones here, and I do encourage everyone to Google. So if I Google FRB sad trombones, then the first hit I get is this, which comes from Emily Petrov's Twitter, originally from Hessels et al. And I think the third hit I get is this beautiful trombone solo by Keith from last FRB 2020, right? But, we've seen that we're starting to understand that there is some sort of relation maybe with some events between the downdrift rate and the duration of the burst, but what's actually causing that? Ray's pointed out that there's some FRBs with this flat PA or a PA sweep. There's one now that's got this sort of subsec, or this order second subsecond periodicity. There's different time structures in the burstiness, right? And of course, if you extend this plot, so this is around 1 to 10 milliseconds, this is around a minute. And of course, we also know that there's a 16, 160-ish, 157 day periodicities. So if we take all that mess of things, and then, we've had a bunch of different explanations brought up this meeting. So these are plots taken from the contributors of session 5A, talking about curvature radiation, plasmoid ejection, fireballs, binary neutron stars, all of this. Some of these are actually getting nicely predictive, right? It's always nice when you have a theorist say that if this model is correct, we should see this, and if this model is correct, we should see that, etc. That's wonderful for the observers to look at. So what I was sort of hoping we can sort of have a discussion about is that there's a whole lot of observables to fit, right? Are there any that we think are more promising for improving our understanding or not? And again, pointing out that we haven't answered this, as far as I'm aware, definitively the emission mechanism for normal pulsars yet, despite having observed them for a long time. So do we actually think this is a tractable problem? I mean, even if it's not, we're going to try. This other question I have about, should we be focusing on these very rare events or whatever an average FRB is, right? And maybe are we at the point now where we need to get all of these people in a room, right? Another theorists who think they can explain the emission, and a bunch of observers who can say, well, what about this? What about that? What about this? And have a very specialized discussion on this. So I'm going to keep this up here, but at least share my screen in a less, actually what I'm going to do is going to stop my share and I'm going to change to sharing the application itself. So I can potentially also see other things at the same time, but apparently that's not possible. So I'm going to just quickly screen share again. Although I'm not even sure it's worthwhile me screen sharing. I wasn't showing anything useful. Discussion time. So Sergey is commenting to the panelists about the recent discovery of circular polarization and how important it is because it's not very easy to produce in shock models. Is that correct? Is there someone who's an expert at the shock models who can say to what degree circular polarization can or cannot be produced in such models? No one is willing to stick their hand up to say that they are. And yes, neutron stars, not neuron stars here. Okay, so no one's willing to favor shock models, apparently. No one in this session. Let's see if we can keep that as an open question. So I do know that there was a lightning talk by Maxim, and Sergey, you clearly know Maxim. So he was pointing out in very strong language that things like the frequency downdrift are 100% predicted and well understood and clearly indicate certain emission mechanisms from magnetars. He wasn't mincing his words in his lightning talk. Can you speak a little bit more to that, since if you're familiar?
No, I'm afraid that I cannot actually.
I'd be willing to stick my neck out, Clancy, and say that that at least for the repeaters, the phenomenology that we've seen has been encouragingly homogeneous at some level. They basically all show the sad trombone effect. They're typically highly linearly polarized. We can, of course, talk about whether there's some circular polarization as well, but compared to the diversity that's just seen from pulsars in general, I think the repeaters look more homogeneous in their properties. So I think there is potentially more hope in that case to understand the emission mechanism maybe than from pulsars, or at least have confidence that you're seeing something very similar from them. In pulsars, of course, we're always hampered by geometry. That a lot of the diversity that we see is just the way that the pulsar is pointing to us or not. Maybe the homogeneity of the repeater properties suggests that they have very similar geometries, or maybe all pointing very much towards us. Be interested if people have comments about that.
I don't see any comments about that yet. There was, though, some explanations about the beaming, right? The relativistic beaming with respect, the time delays from emission to observer. And that seemed to be a relatively good explanation for some aspects of repeater behavior, if I recall correctly.
I haven't looked at Maxim's lightning talk, but I would imagine that he is strongly promoting the idea that it's a radius to frequency mapping effect. And I think a lot of the people trying to model the sad trombone are saying similar things. I mean, that was even in the early observational papers that was discussed in more hand-wavy ways. It's something that we see in like flare stars and the sun as well. It's kind of a generic thing that you see in from coherent emission from some kind of magnetosphere.
So if that's the case, and we do, and it appears that we do not see such behavior in once-off, or apparently once-off FRBs in general, right? And it does seem like, as Ray showed, that you can use this in a predictive way, right? And say, oh, now we've seen a sad trombone that's apparently a once-off, but I bet it's a repeater. Now, does this mean that if there's some radius to frequency mapping effect going on in the repeaters, if they do come from the same population and there's just some kind of aging effect, let's say, that makes things less powerful and rare as they go, why would we not see such a radius to frequency mapping for these once-off bursts? So there's the question.
That's a good question.
Speaking of questions, so Sandra is asking, Sandra is asking if someone, or if we, I don't know who the you is here, Sandra, I have no expectations of what FRBs do at all, right? I just look for the things. So you're asking, do we expect it to be the same emission mechanism or a similar boosting mechanism? At least the work I was referring to, it was not making any assumptions about the emission mechanism itself, right? I think it was simply saying, supposing a thing is happening at lower radii and a thing is happening at higher radii. Is that a fairly correct characterization of this, Jason?
Yeah.
Yeah.
Yeah, I think the general picture is that the emission starts at some low altitude in the magnetosphere where the plasma density is higher and the ambient magnetic field energy density is higher, and then it's propagating outwards. And that all seems very sensible. What I still don't really understand at all in the case of the repeaters is why we see that the emission turning on and off, why we see subbursts, why we don't see a more continuous propagation outwards. It really seems like the mechanism turns on, it shuts off for a while, and by the time it turns on again, it has moved to a higher altitude, it's moved further away from the central engine, and then it lights up again. And that could just be, some microphysics related to, having coherence conditions that you can actually produce the coherent emission, and maybe you can produce it for some limited amount of time before you disturb the emitting region, and the coherent emission shuts off again. But I haven't seen too many very convincing explanations for why that happens.
So I'm seeing a bunch of, a fair bit of silence on this discussion at the moment regarding, maybe at the moment it's we either don't have the right people in the audience from the theorist perspective who want to jump up and use this as a soapbox to send forward their theory, or they're too polite to do it.
I get the impression, Clancy, that people are very wary of the history of trying to understand pulsars from 50 years, that they don't want to wade into it for FRBs. They just want to, at a more superficial level, kind of understand what they are.
Yeah. All right, so Sergey's got a question to throw out to everybody, which is, are there ideas about the DM increase in FRB2021? And so say, except that this corresponds to the specific stage of a supernova evolution. Right. So what you're referring to there, Sergey, is the idea that this thing's embedded in some expanding ejector. And is that what you're referring to, or do you want to take over the mic?
The only idea, actually, in one recent paper, sorry, I don't remember which was, they suggested that it corresponds to some stage of the supernova remnant evolution when you start to collect more matter outside the expanding shock. And so it is expected that dispersion measure can be increased. this moment, but other ideas, because everybody was waiting for decrease of the dispersion measure and to say that, aha, this is a young supernova remnant, it's expanding, and so it's everything. And people found quite an opposite thing. And is it an interesting feature in your opinion? Because it really contradicts to early expectations.
So there's also the idea that if the matter is expanding into non-ionized material, let's say it's some star-forming region and there's still some dense clouds, then it might be then the ejector might be ionizing the material as it goes, right? So when the shock runs into more material, you're turning non-ionized gas into ionized gas, and in theory that could lead to an increased DM even as the shell expands outward, where normally you would naively think that when the shell goes outward it gets thinner.
So I think related to what Sergey is asking, I mean, Casey gave a presentation about persistent radio sources, and there's apparently a persistent radio source, compact persistent radio source associated with another repeating FRB, and it looks like in the late breaking news talks that that D. Lee will present the case for this source being kind of like a twin of the first repeater, which is good. It's good to have two of a feather. But I think, and I was talking to Casey about this in the last session as kind of a comment question to him. I think we still don't really know what this persistent radio source is and what it means. And as has been discussed for years now already in the literature, I can kind of see two possibilities. On one hand, you could have, you could take the approach that you say this is some kind of nebula, supernova remnant, or magnetar wind nebula around the source. And it must be a very, very young source, and we should see evolution of this nebula. And we have seen evolution of RM and DM, maybe not exactly what we would expect for an expanding nebula or supernova remnant. What is difficult to swallow about that hypothesis is that it would have to be about 1 million times brighter than the Crab Nebula. So that's that's not joking around, basically, if you're going to be 1 million times brighter than the Crab Nebula, because that's already one of the brightest radio sources in the sky. But then on the other hand, it could be circumstantial, right? It could be that it's like the galactic center magnetar that we have in our own galaxy. That is essentially, we are seeing a fairly young source, but it's just in a nuclear star forming region where you have a massive black hole at the center. In this case, because it's a dwarf galaxy, it would have to be an intermediate mass black hole, maybe 1,000, 10,000 solar masses or so. You see a compact radio source because it's maybe accreting at a very low level. Then the radioluminosity of the persistent source is not a big deal at all because it's puny compared to a full-on AGN. But then the FRB is just there by circumstance. It's there because it was formed through potentially core collapse. It's a youngish neutron star. It's doing its thing. The DM and RM variations are similar to the ones we see from the galactic center magnetar, in the sense that you're in this very dense ionized region around this massive black hole, and that's that. So it's unclear to me, how important the DM, RM variations and also the persistent radio source are, because you could really interpret them as being fully circumstantial, or you could say, aha, this is really, really probing the local environment around the source in a way that's telling us about what type of source it is in a deeper way than just we know it's in a star forming region or something like that. So comments on that. I'm sure people have comments on that. If like Sriharsh or Mohit or other people are still online, then I'm sure they have comments on things like that.
So we do see some comments from Laura, Sander, and Vivek. So Sander is saying, we have this wonderful website with FRB models. Do we also collect the observational constraints? Can we? Is anybody matching the theories with observational constraints?
Yeah, it would be good to have I think it's a good idea. It'd be good to have like an FRB phenomena catalog.
Yeah.
Also, Ron's got his hand up, so I'll see if I can ask him to.
I was just going to follow up on Jason's question about the persistent radio sources. My recollection is, but I may be wrong, is that there are some really high resolution VLBI observations that say they are very small. So that does mean they're not just emission from a starburst region. I think they're too small for that.
Yeah, that's right, Ron. Yeah, it's consistent. So for the first repeater, the constraint is 0.7 parsecs. So so that's fine. I mean, that's like a fifth or so the size of the Crab Nebula, so it's not large. Oh no, wait, sorry. I think it's still larger than the Crab Nebula, but it's, you know, nebula size-ish, supernova remnant size is a constraint, but it's also consistent with being, you know, the core of an AGN or creating massive black hole. But it's certainly not star formation. That's true.
So I want to get shortly to the discussion that Laura, sorry, I always want to go back to the German pronunciation of Laura from my time there. But I just want to quickly address the last part of Sanders' question, where he's asking, you know, is anybody matching the theories with observational constraints? Well, I guess yes, that's what we're trying to do right now. My feeling is it's too early to have to do the equivalent of a review article that is that is summing up, here's the explanations and here's the constraints. I mean, clearly there are some, but I think, yeah, and it would be interesting to try to do that.
One of the things that keeps me up at night, though, is it doesn't seem possible to come up with a killer observable that really differentiates between models. I mean, the discovery of a repeater, that was a no-brainer. That certainly ruled out some models, thank God. But even you know, this nearby source in M81 in a globular cluster, boy, there's a lot of things it could be in principle.
I will give you an idea for a killer observable. Suppose we see like actual neutron star type periodicity with P and P dot and P dot dot, and we also track the orbit or whatever, if it's in orbit. Then you know all the story, right?
Yeah, if you can come up with a timing model, boy, you know a lot. Yeah, but if say you just get a period, say that the like
no, not just a period. You need all the shenanigans.
Yeah, exactly. But we don't have all the shenanigans. And if you look at the chime source that has the 200 and whatever millisecond period, what if that burst is never seen again? We have something interesting. We know that there was a period, but we'll never have a period derivative. We'll never have a Doppler shift of the period to get an orbit or anything like that. But yeah, one of the reasons why we've learned so much about pulsars and why we've been able to use them for such great astrophysical and fundamental physics tests is because you can have a timing model, but we're very far away from that with FRBs so far.
Why are we far away from a timing model?
Because there's no periodicity that we've detected in the repeaters, no strict periodicity.
But that doesn't mean we are far away from it, right? It just means that we need either to observe more repeaters and to think how to get a timing model, no?
Well, I would say that the distance from what you're describing is unknown, in the sense that we might never have that, or never have that for the majority of sources. Maybe we'll get that for one source, and then you're satisfied because we were able to do it for one source. But I mean, we have detections of like the first repeater where there's over 100 bursts within like half an hour or so, and that certainly is informative, but it doesn't provide a strict periodicity or timing model to work with.
So I think this leads quite well into the comments by Laura. So first, Laura began by noting that the estimated age from the RM evolution of 121102 is inconsistent with the period of a supernova, in which case the DM should be increasing. So that's excluded. That's good. So there's one observation that's excluded, and then pointing out that it could just be the local medium's patchy and move behind a bubble. But then the discussion continued where Vivek was pointing out that it's important to track and change the change in scattering properties, and in general all the properties of 121102 with time, right? And clearly, if Barak, you want to have some search for evolution, well, as Jason's noted, you don't have a very well defined, you've got this broad time window for 121102 when it's active and a broad time window when it's inactive, but it's not this very hard pulsar like timing. But maybe if we do keep on observing the thing for long enough, then and across different frequencies, right, where we might see emission offset times at different frequencies, we can at least get a better idea. And maybe we will find some evidence for increasing or decreasing periodicity as such. So it's definitely worthwhile doing.
Shriyarsh is saying some provocative things, so I really think
Jason?
we should just put him on the spot.
Oh yeah, I was going to say, didn't Chime report a periodic repeater like a week ago?
Yeah,
Maybe
Shriyarsh, do you want to explain
tell us
the
about that?
observation?
No, what I'm saying is that it's not really provocative. I'm not sure why you said that. All I'm saying is that for RRADs, where the P dots are typical of pulsars, and we see periodicities within a few burst detections. You get 5-6 bursts, and you have a good idea of what the period is, or maybe at least the harmonic. With repeaters, now we have with 121102 we have 2000 bursts or whatever, and with R3 we have I think 60 or so bursts now, and there is no periodicity. That makes me feel that this is truly a random process. I mean, it doesn't. I completely agree that if we have enough number of weird parameters, we could fit 60 bursts with some very complex timing model. But then you have to figure out what is the truth of that timing model.
So what about the general on-off period of the various repeaters, right? So the two that we have lots and lots of bursts for, I believe, we do see active periods, inactive periods, and presumably the length of those windows and their duration is telling us something about them.
Yeah, they're telling us, I don't know what.
But potentially, if we look for long enough, those times might change. And again, if they do, what would that tell us?
Right. I mean, if we are detecting, if the change in pulsar rate is very large, right, between the on and off window, and it's very sharp, then yes, you can probably tell the difference in the timing. But I don't think that's happening anytime soon.
Shriyarsh, Amanda is bringing up the Chime periodic burst. Do you want to explain a little bit how that still jives with your thinking?
Yeah, am I misunderstanding that paper, Shriyarsh? I thought it's claiming that the components are very periodic separation.
Right. Okay. So in my mind, we were discussing about the periodicity of repeaters, and I was focusing on R1, R2, R3, and trying to understand strict periodicities from those. This one, yes, definitely there is a strict periodicity. This is if somebody has not seen this, you should go and look at Daniel M. Keely's talk. So we
put the link in the chat as well.
Yeah, so we discovered an FRB which had multiple components. We could fit anywhere between 9 to 14 scattered components, and there is a very strict periodicity of 200 milliseconds to it. Well, we don't quite know what the periodicity is due to. It could be, precession. It could be just a rotational period, and then the pulsar is active, pulsar or whatever neutron star is active for a certain period of time, and then it disappears. And as Jason said, it might be gone forever, and we would never know. So if you have, if this emission is coming from an orbital motion of two merging neutron stars, then it's just gone, right? We're not going to see them ever. Clancy asked in the Slack whether we call this a repeater, and that I think is a provocative question. We don't know whether to call this a repeater or just subcomponents of a single burst. But I think that's sort of a very detailed point. But that is what I was getting at. I was thinking about proper repeaters like R3 and R1 and all the others, not this specific burst.
Yeah, I guess there's someone else commented, Surya commented in the chat as well, and I would have the same question, which is how do you separate between repeaters and components? Is it because the time frame is so short, so you say, well, we just think of these as multiple components and it's not a repeater? It may be a naive question, but to me, it's not clear why you wouldn't just call this a repeater with very short time scale between repetitions.
No, you're absolutely right. I mean, there is no clear boundary. One of the things you might say is, if there is a sort of, we had the same question which came up when we saw these multi-component bursts from repeaters, and most of them were downward drifting, and a few we saw seemed to have one component which was at lower frequency which came first, and then another component at higher frequency which came later. But then there was no sort of bridge of emission between them, and then the question is this really a upward trending burst, or is it just two separate bursts, right? And I don't think there is a clear answer for this. There was one talk, I forget who presented it, which showed that the waiting time distribution between bursts, and you could clearly see that there is a bimodal distribution between about 0.1 second, with a separation at about 0.1 seconds. Perhaps that is a good number to work with. I mean, that could be specific to that particular repeater.
Yeah, that was Jansky Flares who presented that. It was one of the figures that was on the slide.
Yeah.
But yeah, that kind of suggests that that tells you what time duration you call an event, and then what time duration do you call separate events.
I actually think that was a wonderful result, because it does give us a reason to talk about subbursts versus separate events, right? Whereas if the distribution just continued out, then we wouldn't be able to make that distinction legitimately.
Yeah, I agree.
Sriharsh, sorry, just one more thing about this very interesting periodic burst. I think it's important for everyone to appreciate that it's twice exceptional. And you can correct me if I'm wrong, Sriharsh, but my understanding is that it's really exceptionally highly scattered compared to other bursts that have been found by CHIME. So not only is it not only does it last very long with many components that are also periodic, it also has this huge scattering time of about 300 milliseconds or so. So it seems like it's a different beast in many ways.
Indeed, yeah. It was quite surprising that it was quite surprising, because the sensitivity of CHIME drops quite significantly when you go to wider pulses and higher scattering times. And so it is quite significant that we found this in the first place, but it is quite unlike any of the other FRBs that we have found.
So I'm not sure where Clancy went, but Laura, you had a number of comments in the chat, and you could maybe speak more about this bimodality as well, because Yosha is working with you.
I can. I'll try to be quick, because it seems like people want to move on to the multi-wavelength stuff. I guess my general comment regarding to Sriharsh's point about the RRATs is that yes, you can find a period in RRATs very quickly, but RRATs tend to be slow rotators and have very low duty cycles. If you have a low duty cycle, so it only emits over a small range of rotational phase, and it's fairly straightforward to find a period. Actually, the Niner repeater, the Niner chime burst that you just talked about is an excellent example. I mean, Daniele showed this phase versus basically the folded residuals, as we would call them in pulsar world, and the phase jitter was, I mean, astonishingly low, almost too good to be true, really. And of course, if you have that, then finding a periodicity in 9 bursts is straightforward. So I think the answer is, if there is some sort of strict periodicity among, let's call them classic repeaters like R1, R3, et cetera, I think it's telling us that either you have a more complicated window, or you have a much wider range over which it's emitting. The downward drifting could be complicating things, because that could be, depending on, maybe you're moving through a significant fraction of the magnetosphere. Who knows? Anyway, so I think there's still hope, but I think the simple answer, I think we've ruled out the simple case of a low duty cycle. And with regard to Yosha's really nice result, I think it's telling us that there's an event time scale which has to do with the emission process, and if it is a rotating neutron star, then it's probably telling us roughly what the time it takes for the one rotation to pass us, and all the other ones are the events between the rotation. But it could be, if it's a synchrotron maser model, then I'm guessing that left peak, the sort of shorter one, is just the characteristic time scale of a burst hitting the material, and then everything between that is different burst. So I think it is telling something very interesting about the time scales of events, for sure. And I think does help constrain a periodicity, if there is one.
Yeah.
In my opinion.
And Laura, you raised another important point that I think the way I would put it is, the sad trombone effect. It suggests that the emission region is changing with time during the burst, and as you say, perhaps it does so over a range which is a significant fraction of the size of the magnetosphere. The fact that we can time pulsars is kind of predicated on the fact that the emission region has some boundary to it, that on average the emission occurs within some box. If you average pulses together, then the location that the radio bursts are coming from is intimately tied to the neutron star itself and locked in rotational phase. Just the fact that we see the sad trombone effect suggests that the emission region is bouncing around, and that's a big issue for finding periodicity.
So I think I might try to move the discussion on from here, simply because we did want to at least address the multi-wavelength and multi-messenger aspect. So I will technically share my screen, although there's not very much sophisticated I'm going to actually present. One of the main reasons was I haven't actually been able to see plenary session 6 yet on multi-messenger observations, right? So I'm going to talk about these very, very basic points, which is, so far it looks like multi-messenger people are looking at X-ray, optical, gravitational wave, and other wavelengths, right? And clearly this is another way of looking at the origin of things. We saw, from the soft gamma repeater, right, the galactic one, that the X-ray radio correlation definitely told us something there. And my 3 points down the bottom are meant to sort of start a discussion on how we can facilitate this. So I think in general, we're all agreed that the closer an FRB is, the easier it is to do multi-wavelength or multi-messenger observations on it, right? Then there was this question, somebody else, I forget who initially raised this, about do FRBs have radio afterglows, but essentially doing commensal observations, right? Looking at exactly the same time, because if something's a fundamentally rare event, then, or it's a once-off, it's very difficult to then go back and look at it later once you've already, even if you've localized it perfectly. And then the other general question, how to facilitate this is there any new instrumentation we'd like to build, whether that's on the radio or non-radio side? So suggestions for any of these or new points would be most welcome. And I'm going to stop sharing because they're pretty basic points and I hope you can all remember them. And I want to look at the chat.
Yeah, I want other people to talk, but maybe I'll inject one point that Ryan Shannon brought up during the multi-wavelength session, which was really good, by the way. Lots of really interesting talks there. He brought up the point that, yeah, definitely, nearby sources are good, but don't be myopically focused towards that, because really like high fluence events are also important. So if you have an FRB that's much further away than, tens of megaparsecs, but it's producing kilojansky or 10 kilojansky radio bursts, then those can also be really interesting for trying to get multi-wavelength detections. And kind of the overarching story here is I think any multi-wavelength detection is going to help enormously with understanding what's going on.
Yeah, and I guess for the X-ray observations, there was a talk about non-detections using NICER. So, and they said that the non-detection, this favors shock models that are more efficient for the X-ray emission. And they claim that it favors magnetospheric radio emission from older magnetars. So basically disfavoring young magnetars because of lack of X-ray emission.
Adam has his hand up.
Yeah, I was just going to say that, I think the prediction of like a coincident hard X-ray burst with the radio FRB itself is pretty strong from some of the models. And so getting the strongest either detection of an equivalent X-ray burst with a relatively bright FRB, as opposed to the fainter ones that we've been able to do that for so far, or else a much more constraining limit that says that the ratio of X-ray flux to radio flux is a lot lower in one of these, I don't want to be prerogative, like real FRBs, cosmological, much more luminous FRBs, would be a pretty big deal. but I don't see any way of doing that apart from getting lucky with either an X-ray telescope pointing in the right place, so with the deeper, more sensitivity at the time of a regular FRB, or just catching a really, really, really bright FRB. So those are two potentially orthogonal ways to go at it, but I don't think either of them, I find it hard to see how we can do either of those things efficiently. I think it requires the universe to provide.
Yeah, the not being able to follow up because the latency is, well, not being able to trigger an X-ray telescope for a bright FRB is a real issue.
And I suppose that there's not too many X-ray telescopes that want to point to the one random location for a few months whilst tracking the same position as a radio telescope that is doing a random search.
No, the best thing we could come up with, I think, was if you had a very active FRB that was, had a high burst rate of very bright bursts intrinsically, as opposed to just apparently because it was very close. That would be an obvious thing to target, but then you're obviously targeting some extreme outlier as well, and so how generalizable those results would be might be questionable. But I think it would still be a good place to start. But we need that source first, I guess.
So were any results presented in session 6 on X-ray attempts to look at the M81 FRB?
No, I don't think so.
No, I think those are on the cards.
Yeah, I know there are observations in the bag. Yeah, and in terms of like persistent emission, there's stuff already said about that in the Kirsten et al. Paper, but there are some nicer observations during radio bursts that will be interesting. Sriharsh, you had your hand up already.
Yeah, so I just wanted to add to what Ryan said about following up the brightest and nearest FRBs. I mean, just based on the rate of FRBs and X-ray transients, we know that most garden variety FRBs are not going to have X-ray counterparts. But I would also like to add that we should follow up even anything that is rare in any dimension, not just brightness or XSDM, should be followed up. I mean, the weird structure which we saw for this 200 millisecond periodic FRB, that would be an important thing to quickly follow up. So the point I was trying to make is that the XSDM and brightness are very easy things to note, that you can see, okay, this is really bright or this is really nearby. But we should try to focus on techniques where we can identify anomalies in other dimensions very quickly and alert X-ray telescopes.
So talking about anomalies, so clearly you mentioned this recent CHIME one with the sub-second periodicity. As has been noted before, there's, for a very long time, every FRB had its own little anomaly, right? Ryan would like to call them their own special little snowflakes. Do you have any other suggestions of quick observables that would be anomalous? I mean, so clearly the ones that every observer detects, there's, the fluence and then DM, right? So I guess you could look at one that's particularly low or particularly high DM as an extreme. Scattering, would that be one that would be on your list?
I think so. I mean, it depends on each telescope's selection function, right? So it depends on what your telescope is sensitive to and what is considered an anomaly in your view, right? So I think it will depend significantly on that. And I was thinking of something like a proper non-parametric anomaly detection from machine learning codes or something, which I'm not an expert in, but I would like people to explore that I think would be useful.
That's a good point. All right, Sandro, I think you had your hand up.
Yes, so this is a bit about following radio and, for example, X-ray bursts. So you said we can probably not convince some X-ray telescope to point at one point in the sky, but could we convince some radio telescopes to point at the same directions as the X-ray telescopes are already pointing, to find something there? Is there anything we could do there with tracking other schedules?
Well, I can personally say that I'm working with eRosita And I know there's another couple of members, I think, here, Laura's part of that too, to use Effelsberg and Parkes to say whenever they point at a position of a known FRB, to make sure that Effelsberg and Parkes are pointing at it too, so that you can have at least some simultaneous X-ray radio coverage. I actually don't know if Parkes is fast enough to track E Rosetta across the sky in its pointing direction. I guess it probably would be. The problem we've been having there is that E Rosetta has not been able to give us its observing schedule sufficiently far in advance for us to know when we want the observations. But no, that's absolutely something we could be doing. And perhaps that would be an excellent job for some of these relatively smaller, underused telescopes. So I forget the name of the presenter.
I wouldn't say that they're underused anymore, Clancy.
They are used now, but this is something they could do. And also in the design of our next generation of telescopes, we should take this into account. So we've been doing this with LOFAR to follow up X-ray bursts as well, but we're not yet quite fast enough to really catch the ones at the same time as the X-ray bursts would occur. Or maybe you even need to catch them before, which is even more difficult. So things like buffers, fast scheduling, those kind of things are things we need to take into account if we want to get into this game.
Of course, the other game we can play, right, and this is what you can do even without having commensal observations, is simply to say, well, we know what the observed rate of FRBs is on the sky, of order 10,000 a day above some threshold, pick a number. And then it seems like population models are saying that, of order 100,000 per gigaparsec per year in terms of number rate. Now, even if let's say you're in control of E Rosetta, for instance, you can measure the rate at which you see weird extragalactic transients, right? And so let's imagine that let's imagine if E Rosetta saw, I forget what the field of view of E Rosetta is, right? But imagine if they saw the equivalent of 1,000 X-ray transients per sky per day, right? So they measure some number and they do the maths and they work out there's 1,000 weird X-ray transients per sky per day. Well, if we see 10,000 FRBs per sky per day, then that says that, well, at most, it's about 1 in 10 FRBs will produce an associated X-ray transient. Thanks, Sergey.
Above the threshold.
Yeah, so you can play this sort of relatively simple game and say, well, even if, we should already have some idea of a chance coincidence. And then you can always try to get clever and say, okay, well, we see FRBs from the very distant universe, so maybe if we narrow it down to the 10% of the nearest FRBs and so on.
For the people that missed the session, there was also Aaron. Aaron was giving a talk about X-ray follow-up of FRBs. So if you send him when you detect an FRB, then he can be on source within 20 minutes or so, on average, observing X-rays.
All right, at the moment, I want to just click on the archive link that Sergey has posted. Sergey, do you want to give us is this something that you're involved with? Do you want to give us a quick summary of that?
Well, yeah, the probability is low, that's the summary. So you cannot expect many situations when Rosetta is pointing somewhere and this area is simultaneously occasionally monitored by a radio telescope. So I think that it's much more profitable to focus on nearby repeaters than to just look through the whole sky for the chance of for a chance to observe simultaneous bursts in X-rays and in radio, unless you have two surveys. So it would be quite easy to cross-correlate, I don't know, LaFarce or something with or STARE with all sky monitors or bright white surveys in X-rays. But with pointing observations, the probability is not that high.
So is there some way that we as the FRB community can motivate the X-ray or optical or other communities to build new instruments that would enable perhaps multi-wavelength searches. No, some very wide field of view X-ray telescope or an X-ray telescope that's going to sit, be geospatially located above CHIME and stare in the direction where CHIME is most sensitive the entire time.
Well, I suspect that you cannot obtain significant sensitivity. Well, we have Fermi now, for example, and we have many all-sky monitors in gamma rays with smaller sensitivity. But if you make an all-sky monitor in X-ray or in gamma rays, typically you are sensitive to sources at distances of few megaparsec or maybe tens of megaparsec. So the volume is much smaller and then can be covered by radio observations of FRBs. So it's maybe interesting to discuss, but I don't expect that it would be easy to invent a new instrument in X-rays which have high sensitivity and large area simultaneously.
All right. So yeah, okay. It would be nice to have though, but it's something I think we should consider, right? If someone does come up with an interesting idea, we can push for it. I completely agree with Vivek's comment that we should build more MWA-like wide field of view telescopes thereabouts. And I'm just reading Fabian's comment about Meertrap and Meerkat commensally look at various well-studied optical and X-ray fields too. So when you say commensally, Fabian, does that mean that Meertrap, so Meertrap is looking at these well-studied fields at the same time as the other surveys are being carried out? Yes, okay, cool. And then a question that Ray's been asking, he sent to specifically the panelists, so I'll repeat it out here. He's asking if it's realistic to use FRB real-time detection as the trigger for a multi-wavelength campaign for some particular target. So I guess this would be saying we've got an FRB, we've identified that within a few seconds, and then let's immediately trigger, let's say, an E Rosetta to suddenly turn around.
So I guess that was exactly the Superb survey was doing. So we were finding FRBs in the real time, getting notifications within 10 seconds of the burst, and then sending emails. So the triggering was not automatic, but we had MOU with a bunch of observatories, optical, X-ray, and multi-messenger telescopes, and then we'll send them an email, and they all look at that patch of the sky to look for clues at other wavelengths.
Okay, so we've only got about 10 minutes, I think, left in the discussion if my computer clock's accurate. I mean, I know my computer clock's not accurate, but I think it's about 8 minutes fast. Amanda, you wanted to present the last topic, I believe, which was essentially asking what we would need to know about the population for instance, to inform cosmological studies. Would you like to take over and introduce that?
Sure. So I don't think we actually, I don't think we even need slides for this. So the question is the following. If you switch around a little bit and take the stance of someone who's more interested in or somewhat interested in looking at FRBs and using them as sort of collective rulers, as a way of measuring the universe on very large scales, or measuring answering questions about the very early universe that you cannot answer accurately or perfectly with other tools. What sort of observations do we need from FRBs that would allow that? So the very obvious blunt example is that if it's impossible to see FRBs past a certain redshift, if they don't exist, if there's some physical mechanism that only allows for FRBs to form in the recent universe, then we cannot use them for very early universe questions. There's no way to look at, well, we might answer early universe questions because we can look through the expansion history of the universe, but there's no way to say, take a large sample of them above redshift 3 and talk about helium reionization. You'd have to be extremely clever. So I think that's sort of something, I don't know if others have interest in this sort of ideas, but that's something where the source, I think it becomes important.
So here was a comment I was going to throw out there as an interesting question. I was hoping Brian Gainsler might actually be part of this session for this. So to get, if it's neutron stars and magnetars, right? Magnetars and neutron stars get their magnetic fields from the star or stars that they're birthed from, which in turn get their magnetic fields mostly from the gas cloud that they were part of. And then through various complicated mechanisms, galaxies have their magnetic fields spun up over time. So how far do you have to go back into the universe before you expect significantly less magnetic neutron stars and magnetars, because there hasn't been enough time for the magnetic fields in galaxies to evolve? For instance, could it be that there's neutron stars, you know, right back at the birth of stars, but they're not sufficiently magnetic to produce bright bursts?
Right. It's a good question, I guess, and hopefully the second session of this is someone asks the same thing of Brian. I'm not sure because I don't understand enough about the formation of magnetars. I guess my concern was that there's a selection bias, or to put it another way, there's a selection limit, in that an FRB would have to be so bright to really see it beyond redshift of 5 or 3, that there's sort of two issues. One is, as you're saying, can the source truly produce them? Do these sources exist that far back? And the other is, would we be able to see them even if they did?
Yes, because if spectrum is very, well, relatively narrow, then simply because of redshift, it can go down to 300 megahertz and sensitivity might go down because just LaFar or, well, few instruments can observe it.
Yeah, so that's certainly an observational effect. Actually, the observational effects get very annoying, because if you have something that's intrinsically got a bandwidth of 200 megahertz, or 200 megahertz, say, and that gets compressed to, say, 50 megahertz, then your sensitivity drops just because most FRB searches look over all the bandwidth, right? I know that Previa's been doing a lot of work to do subband searches with the ultra-wideband system. But if we're looking for distant universe bursts, maybe we do need to be looking for narrow bandwidth things. And
yeah, and ending my comment about magnetic fields, I just wanted to speculate that since you have galaxies and normal star formation, you can expect more or less normal magnetic fields, because galaxies formed simultaneously increasing its magnetic field due to dynamo mechanism. And only stars formed before galaxies might be different, and they might form different binaries. And I just coming back to Magnetaries, if I have a second, I want to show you one figure, because recently there was a nice paper. Can I show it better? Yeah. Oops, sorry. There was a nice paper where people found the star, which definitely was the result of coalescence. And it has very large magnetic field. So just with the flux conservation, you naturally obtain magnetar scale field. And I just wanted to show it as an argument in favor of the idea that magnetars are born, even normal magnetars are born in a specific channel, maybe in a channel which involves coalescence of normal stars, or anyway interaction of normal stars and binaries before the explosion.
Interesting. So I've asked, Navin, who actually had a hand up earlier, made a fairly extensive comment. So and there's a few other comments. So Navin, maybe you can repeat your comment and associate discussion verbally.
Sure, thanks, Clancy. Shrihar just responded quickly to that. So the question was, I'll read it out now. The number of neutron star and black hole neutron star detections are going to go up by several folds by the next year. with the LIGO 04 runs. There are a few models of FRB like emission arising from such mergers. Are there any working plans to near contemporaneously cross-correlating between LIGO Virgo gravitational wave detections and the radio telescopes worldwide to relate gravitational wave event to a radio event?
I can say yes, but I'm not allowed to say anything more.
Okay, yeah. And yeah, Shriyarsh also said that there is some collaboration working on that. So yeah, that's good to know.
I see Ron's hands is up.
Yeah, I was going to, I think it was Amanda, it's now getting back a bit, ask the question of what we would need to observe to make observations that were more useful for cosmology. So I was going to throw that question back to Clancy, who shows what he calls the inverse Macquart relation, where by having higher DM, you don't actually get to higher redshift. But let's change that round a bit, because that's very much a property of the selection imposed by the telescope. And ask the question, if you want to find very high redshift FRBs, what kind of telescope do you build? Now, one suggestion is we go to low frequency, the redshift is then helping you. But my guess, but I'll get Clancy to answer, is I would go to wide field of view and very high sensitivity. And so, for example, it is technically possible to put, say, 1,000 beams on fast. And does that answer the question? Does that get the cosmological FRBs?
So what I would argue, Ron, I guess the point I was making from my modeling about the downturn with the DM is that once you get into the high DM range, you really need a localization to know where the darn thing is, right? I've heard a rumor that the VLA has got a localization of a very high DM thing that is not sitting on the Macquart relation, and hopefully we'll hear about that somewhere in this talk, in this conference. So you would absolutely putting something like a phased array feed on fast would be wonderful, but then you would absolutely also want at least a couple of, I don't know what an outrigger to fast would be, parks maybe, something much smaller than fast, which is nonetheless enormous, to be able to localize it. Because if you're only measuring the DM of the thing, then you might get something with a DM of 3000, and it could be at a redshift of order 3, or it could be a redshift of 0.2 and come from the middle of a massive galaxy cluster. And so I guess my point is that to do cosmology, you not only need to detect the FRBs at high redshift, you want to be localizing them too, to know they're actually the high redshift ones and not to get swamped by all these, uncertainties in selection effects.
Okay, so you gave one answer. You would need, and that's been discussed, in fact, say 3 fast telescopes, each with wide field of view. So that is one observational approach. But I'm saying, have we explored all the different approaches?
I can guarantee we haven't explored all the different observational approaches. Have you got any other ones in mind? If D. Lee was in the discussion, he might be able to say something more about the prospects of more fast telescopes.
You could go for higher time resolution to break a bit the degeneracy with how bright the pulses are.
Remind me how the higher time resolution would help. I mean, you're
so
right.
So if you can detect microsecond pulses versus millisecond pulses, then you can go a few orders of magnitude higher influence.
Yeah, so
lower influence.
It's true that if there's a significant population of microsecond pulses and they obey and they have a similar fluence to the millisecond ones, then yes, that would help your sensitivity. That's true.
But you have to, instead of building a big telescope, you have to build a big computer.
Yeah.
Or go to high frequencies, although it doesn't seem like FRBs are that prolific at 5 or 10 gigahertz. We haven't really searched, though. We don't really have a wide field 5 to 10 gigahertz chime.
If you go to high redshift, then you need to take into account that the emission at the source might change. If all the FRBs are emitting at 1 to 2 gigahertz, then you want to look at lower frequencies.
Yeah, true as well.
I'll quickly chime in here, and I agree with this comment because this is something I've been thinking about myself, that if you are going to detect high redshift FRBs, you're more likely to detect narrower ones than wider ones, just because you're sensitive to narrower bursts down to a lower frequency. So if you are trying to actively design telescopes for high redshift FRBs, you better make sure that you're detecting narrow ones accurately and not using those.
No, that's a good point. Now we're running out of time. There's a couple of hands up, and I promise Sriharsh I'll let him talk, and then Ray had his hand up as well. So let's hand over to Sriharsh and then Ray, and then Jason, I'll let you be the arbiter of when we can cut this off, because at the moment I've got another hour till I have to supervise my daughter. So.
Damn it, Clancy. No, 5 minutes. Let's keep it to 5 minutes overtime. It's like it's a tie game, and we need to finish it in the next 5 minutes.
All right,
I can concede my time. We can move on if you want.
No, speak up.
Okay, so quickly, the thing that keeps me up at night is that, what if there is a LIGO black hole binary neutron star merger, and it happens in the CHIME sky or some other telescope sky, and our FRB pipelines don't detect it? What if it looks different from what we search for? And I mean, Navin's paper, he shows that they could be 500 milliseconds wide, and we simply don't search that. So one of the things we should look into is taking VO events from LIGO and then saving our buffers or freezing radio telescope buffers, so that we can actually save the data and look at it with a fine-tooth comb, because LIGO events are rare. And maybe this happens once a year, you get telescope dead time for a couple of hours, but I think it would be extremely useful.
Thanks for that point, Sriharsh.
Okay, and then I think Ray, you had your hand up earlier, and I think you should have speaking permission. Though I don't see Ray, I can't find Ray now. Ray, you did have your hand up earlier, right? Three, two, one. Okay, no, apparently.
Hi, sorry. I just comment following Clancy and Ron. Actually, the fast people do want to do FRB cosmology, especially for FRB from redshift 1 to 2. We do want to see what's my correlation goes in that redshift range, but it's not easy. As you know, the detection rate for fast telescope is only we only expect to one detection by spending half a month or 1 month. And in addition, as you know, the Chinese government it has such concept to build 6 fast telescope array, but as you know, the fast telescope is not a steerable dish, and how to do via interferometry is still big issue. We don't know how to carry out, in fact, technically. And now, even though we have such concept, but we do not have the funding for that. Maybe it can happen at least for 10 years. So it's not be so soon. We do expect FRB cosmology in the future, but I think the SK should be a breakthrough for such big project. FRB cosmology can be achieved by SKA, not rather than 6 fast.
So Ray, did you just say that because China won't build the radio telescopes quickly enough, we should rely on SKA being complete instead?
Even China is still a member in SK collaboration, but China's government is very ambitious. They do want to build their own SK, and everybody knows that. They have a lot of fundings on and I think President Xi Jinping support is very rare. He's a big fan in astronomy.
Maybe you can find a more positive way to conclude the session, Clancy? Or...
All right, well, if we want to conclude this, I think one of the positive things that we've had lots of discussions. I don't have any very key takeaways from here. I think it's clear that there are instruments coming up that will be able to probe, do improve prospects for FRB cosmology, right? Whether or not it's SKA, it's Krakow outliers on CHIME. Apologies to people who I'm not mentioning. or more fasts, right? So I think that's an absolute positive, and it's very clear that there's going to be a vast increase over the next few years of the number of localized FRBs, right? So I think that's definitely a positive note if you want one there, Jason. As far as the microphysics emission mechanisms, my impression of both this discussion and the talks have been that it is a tractable problem, right? Because if you start with a baseline of what's going on with pulsars and how long they've been observed and the open questions there, you start getting very depressed and give up almost immediately. And I think that...
Can I interject briefly though? I think a lot of the particle and cell simulations that people like Sasha Filipov and Anatoly Spikovsky are doing, they're really actually making traction on the pulsar mechanism as well. So,
yeah, well, I was very impressed by the 3D simulation that was shown in, I forget which talk it was. I showed a snapshot of it on the slides. And then as far as progenitor models, we're seeing, the kind of analysis that Shivani is doing and others about host galaxy offsets. That is telling us something. Exactly what it's telling us is still a little bit open, but the fact that these are clearly associated with the blue region rather than the red region. So if the conclusion is that FRBs are more Democrat than Republican, that's, well, maybe I shouldn't go there. But we are finding out new things about FRBs, right? So if I compare the status of the field now to where we were a year ago, Jason, I think we're very far ahead. Is that enough of a positive note for you?
Agreed. We're very far ahead, but we're 6 minutes over time, so we should stop. Because also the poster session is on, so I encourage people to join in GatherTown as well to look at the posters if you haven't done so already. Thank you everyone for joining. I'll stop the recording now.